Everyone, welcome to your Play Pause It for the week. We're going to be finishing up the notes from last class on causation, and then we're going to do a little bit more with linear regression. So go ahead and grab your notes and have that assignment open, and we'll get started. Don't forget about your benchmark test next week. So Monday, the 29th, you guys want to make sure you have your math benchmark done by the end of that day. Tuesday, ELA. Wednesday is civics if you're in 7th grade, and science if you're in 8th grade. So just so you guys know that I have our benchmark already up there for you as of the morning of March 25th. So if you do want to complete that early, that is in there for you. Just make sure you have it done by the end of the day on Monday. Again, we're going to be covering causation and linear regression. I'm so excited. So this is from last class, and this was just finding the R value. Remember doing that correlation coefficient. So we're going to review that, and I'm going to switch screens so that way you guys can see me put it in to Desmos for you. Here we go. So remember, step one is always to hit that plus button and add a table because we want to go ahead and put in the data that they gave us. This is the part I was telling you, I think, that's usually the hardest because it's the easiest place to make a mistake. I've literally done it before. You'll likely do it at least once. And you just want to make sure you type in the numbers exactly as they're given. Sometimes it helps to do just a once over after you've typed them in. That's what I'm doing right now. And don't forget, you guys, as always, you can pause these recordings, try these on your own, press play, follow along. You can see that in our viewing window, we just saw one dot. So our X values are pretty big, right? So we're likely going to want to zoom out a little bit. There they are. So if you just look at this, I feel like, and you guys would likely agree, it is mostly increasing, right? It's going up from left to right. If we were to draw a line of best fit sort of right through that data, it does look like the dots would be clustering around the line. So let's see what that R value is. We're going to put y sub 1 and then the tilde or the approximate mx sub 1 plus b. Cool, there's that line. Interesting. That makes sense though, because remember that line is going to go right through the data where there'll be the same number of dots under it and above it. So we do have 3 below and 3 above. Now there's 7 dots. Where's the 7th one? Oh, there it is. It's below. So it's kind of an average. You can see this one's going through that dot. Let me make this smaller. So it's not as strong as I thought because the R value is 0.7711. I mean, it's not incredibly weak either. I would probably say moderately strong. So we'll go back to our notes, and it's 0.7711. Grab my pen. So this does tell us that it's positive. We saw that it was positive, right? And we could say it's moderately strong. So when you look at that number line that we looked at, it is pretty close to 1. Okay, so let's move into causation and correlation. You guys may have heard these terms before. This cartoon. Check this out. They're in this boardroom and they're looking at a graph. This is probably a statistician. We'll go with that. And you can see there are 2 lines graphed, sales and shaved heads. So now the guy goes, we found a correlation in the data. Quick, everybody grab a razor. So the more, this graph is saying that the more shaved heads you have, the more sales you're going to have. Hopefully you won't grab the razor and you'll ask questions. You'll say, let me see the data. Here's another common sort of misconception. So have you guys ever heard that if you eat too many eggs, that you're going to have high cholesterol? That was like a thing at one point. You may be too young to know this, or maybe your learning coaches have heard this, but what they actually found is that people who were more likely to eat eggs were adding bacon to it, or sausage, or buttery fried potatoes. So there was a lurking variable. We call it a lurking variable, and something is hiding in the data that's making it appear to have a causation or to be related. So the lurking variable is the side dish. In this case, the bacon. Sometimes we need to be careful when organizations or companies put out these statements because, yes, they've done some studies, and it's not that they're necessarily trying to hide anything. They didn't know about the side dishes for a while. But as time went by and more research occurred, they were able to identify those lurking variables. So now, according to, the world, eggs are safe again. Eggs are healthy again, and they are. And, they say everything in moderation can be healthy for you, but you don't want to eat too many high cholesterol items like bacon and sausage and things like that. But there are things where correlation actually does mean causation. Things like lung cancer, like smoking. We know that smoke causes lung cancer. Like we know that that causation is real. But like think about it. If there's a cause and effect relationship between two things, it's not always clear like which variable is doing the causing. Like what if there's a moderately positive relationship between the number of years employees work at a company and their happiness level? Do the jobs make them happy? Or do happy people just stay at their jobs longer? Chicken before the egg thing, right? So just be wary. So let's try one. So at one stadium, attendance at baseball games decreased every year from 2012, 2012 to 2016. At the same exact time, the price of admission increased. So we could even add a line in here for admission. We'll just call this price. The price increased. Can you explain why you cannot say with certainty that the increase in ticket prices caused the decline in attendance? That might be the first thing you think of, right? Oh, well, we raised the price so people aren't paying anymore. But what could be some other reasons? What could be some of those lurking variables that aren't present on the graph? Think about it. Maybe say them out loud, write them in your notes. I was thinking, there's so many variables, right? That's kind of the definition of a variable. What about the teams that are playing, those baseball teams? Maybe they started losing, and people didn't want to necessarily see a losing team in person. Maybe they watched on TV. I don't know, just speculation, right? Maybe, gosh, I don't know, maybe as the years went by, more people started watching virtually than going on location. I kind of feel like that might be of the past time. Maybe the local economy went into like a downward slump, so people were earning less money. So it wasn't necessarily that the price went up, it's just that people didn't have as much money to spend on recreational items and entertainment. So there's just so many lurking variables that are there. It doesn't mean that it's not a causation. It just means that it might not be the reason or the only reason. Here's another one. Let's try this one. A positive correlation is found between the amount of garbage in a town produces and the population of the town. So a positive correlation, remember that's going up from left to right. So that's saying the more people in town and the more garbage and vice versa. What do you guys think? Do you think that this is likely causation or could there be some lurking variables? This one's probably likely causation. People produce waste. It's kind of one of our major functions, sadly. So we try really hard not to, but that's kind of what we do on a daily basis. We produce garbage, and as the number of people goes up, so does the amount of waste that they produce. So this is likely, definitely causation. I can't really think of any lurking variables. The only thing I could thought of, because they're talking about a specific town, and maybe you thought of this too, maybe the town just got like 3 or 4 new neighborhoods really fast, like a bunch of townhouses or a bunch of apartment buildings. So the garbage went up pretty quickly, right? But again, that's population still. So I'm trying to think of another reason why garbage would increase that doesn't have to do with population. Oh, I was thinking maybe the garbage trucks broke down and they stopped collecting garbage. That might be a stretch. All right, here's another one. A researcher notices a negative correlation, so it's going to go down from left to right, between the number of umbrellas sold in a city and the number of bike rentals. So the correlation is negative. So as the number of umbrellas sold goes up, we can put umbrellas down here. The number of bike rentals goes down. Interesting. Think about that. The more umbrellas that are being sold, the less bikes are being ridden. Why do you think that's the case? Well, we don't really ride bikes in the rain, right? So if it's likely that if people are buying more umbrellas, it means that it's raining. So likely that's why the bike rentals have gone down. The more it rains, the more people buy those umbrellas, and the less likely they're going to want to ride that bike. We could probably debate this all day and think of some lurking variables, but I think that's the most likely what's happening here. All right, so let's get into some regression. So you might see it written as least squares regression or just linear regression. And you guys, the cool thing is like we've actually already done this because you do this the same exact way that you find that R value, except we're going to look at some more information that Desmos gives us. So the cool thing is we're going to do it the exact same way. So we're going to go to Desmos, clear this out. I'm going to put in a table and enter very carefully the values that they gave me. These look like years versus something. I wish I would have put what this was. That's annoying. 45, 51, 57. There we go. You know what? I remember somebody telling me this last year. If you click this little magnifying glass, watch what happens. Ta-da! It like magically puts your window where it needs to be. So there's our data points. And we're going to find our least squares regression line or our linear regression line, y sub 1, approximately mx1 plus b. Okay, now usually we kind of say, okay, what's the r value? And we stop there. This time we're going to get some more information. So I'm actually going to take a snip. There's a cartoon. I'm going to take a snip of all this so we can bring it back with us to our notes here. So check out everything that the calculator gave us. And let's talk about it. So here's, oh, is it going to let me write on top of it? Nope. Okay, there's our least squares regression line, and all we have to do is plug in the values that it gave us. So we're going to have y equals, instead of m, we're going to have m there, see the m, 3.5, x plus b, 6921.2. And you'll usually see this with a little hat above the y, and that just tells you that this is a prediction line. It tells the reader that this is a regression line. So it's not like the actual line, right? Because this is just giving us an estimate of those dots, right? Kind of going through the average of those dots. And there's the, check this out. If we were to graph the line that it gave us, y equals m is 3.5 and b is negative 6921.2. Check it out. Did you see that? It graphed right over the line. That plotted, when we do the regression, the line plots itself, but then we get the actual equation by doing this. Isn't that cool? So it kind of just confirms your work there. Ta-da! Okay, let me go back to our presentation. I don't know why Chrome started to open. Okay, I just wanted to make sure that the recording was still going because I couldn't see the recorder, and I would hate for that to happen. So thanks for your patience there with the recording. Let's do another one. So we are going to plot these data values in Desmos and try to get the linear regression line. So I'm just going to clear these out. We'll hit plus, add the table, and then enter in the values that it gave us. That was fancy. Desmos started to pre-populate for me. It was getting smart. Did you see that? Okay, we can hit the magnifying glass and it will bring us right to our viewing window there. And we're going to do our regression. So y1 approximately mx1 plus b. There it is. There's all the information we need. It's a pretty strong negative correlation, right? Negative 0.98. And we can put in the line it gives us y equals. It tells us m is negative 10.1. So we're just plugging those in for those m and the b. And b is 118.8. And sure enough, there it is. It plotted itself right over the regression line, and that's our equation. So I'm going to bring this over with us. So hopefully you're finding this pretty straightforward, and the steps to put it in the calculator are not too tough. And it gives you a lot of really good information. That R value, again, tells you how strong that correlation is, and then we have the equation there. All right, so we can have some questions asked another way. See how they give us, oh, you know what I should have done here? Which reminds me, don't forget when you write this equation, you will have a little hat above it. And that just tells you, the reader, that it is approximate. It's a line for you to approximate and make projections. All right, so check this out. They gave us a model, a projection model for fuel economy of a car in miles per gallon. So they tell us X is the car's speed in miles per hour. According to the regression equation, what is the approximate fuel economy for this vehicle at 65 miles per hour? So all we have to do, that's the speed, right? So that's X. All we have to do is plug in 65 for X plus, and that will give us the fuel economy approximation, the Y hat value. Cool, so let's go ahead and go to Desmos and do that. There's two ways to do this. We can enter the equation and then find the X value on the line, or you can just plug it in. So let's see, 0.3418. There we go. 36, let's say 36.6, so it tells us otherwise. No, it does not. So 36.6 miles per gallon. So that's a great estimating tool. I bet you a lot of car dealerships have similar equations, or maybe they have charts and tables based on these equations where they can tell the buyer the fuel economy of the car they're going to purchase. Super useful. Here's another one. In a certain region, the equation, this equation, again, we read this as Y hat. And this models the amount of a homeowner's water bill in dollars. X is the number of residents in a home. What would you expect as the number of residents increased? What would you expect the line to do or the water bill to do? Likely we would expect the bill to increase as well, right? More people, they're going to be using more water, they're going to be taking more showers and baths and cooking water and all of that. What does the slope of this equation represent? So here's the slope, remember the m value. and X represents the number of residents. So for every one resident, that bill goes up $19.485 per resident. So that's the variable. That's the thing that's changing, the number of residents. So if you plug in 2, it would be almost $40 and so on. So that's the per dollar fee, the dollar fee per resident. You could say money per resident. That's what the slope means. And that's it. That's all they wanted. Okay, so now that we've done linear regression, let's try quadratic regression. The cool thing is it's pretty much the same. The only difference is, with linear, we used this equation, right? Oops. Right? Well, for quadratic, we're going to use a quadratic equation, and we're going to use it in standard form. So it's ax squared plus bx plus c. That's that standard form of a quadratic equation. And it's going to give us all the same information, the same way. So let's try it. Go to Desmos, enter in our table. This is a horizontal table, but we're still going to put it in vertically, so be careful as you're entering. 4, 5, 6. And some decimals here. And negatives. Man, there's so much room for error here. And I don't have anybody here with me to tell me if I did it right. So I'm going to double check my numbers. Okay, that looks good. And there's our, ooh, see, it definitely looks quadratic. And let's go ahead and do that regression. So y1 approximately, whoops. Now instead of a linear function, we have to put a quadratic function. Let's see, plus b. It's so cool to see it start to form. Plus c. There it is. See how it's going through the middle of the majority of those dots. And if you wanted to, you could find the r value. We could just take the square root of this. It's funny how they don't give you the r value on this one. So here's the a, b, and the c value. So to get the function, all you do now is plug a, b, and c into the equation. So we would have y equals a is 1.01667 x squared plus b is, I'm going to do minus 6.12143 x plus c. And you don't have to do this step. I just want to show you how cool it is, because it does in fact go right over the predicted line. Because I mean, that's what it is. But you take these A, B, C values, plug them in, and you have your equation. You have your model. So now you can plug any single x value you want in there, and it will give you a predicted value out. So this is our y hat equation. Let's write it. I feel funny saying hat. Y hat. I don't know, it just feels funny. Y hat equals, there we go. All right, let's try another one. Oh, you know what? Hold on one second. So this actually did say to round to the thousands place. So remember, the thousands place is the third decimal. So let's just fix this to be accurate. It should be 0.17 minus 121.01667. plus 162, right? There we go. Okay, last one. Determine the equation of the quadratic regression curve. This sounds so fancy and formal, but you guys know how to do this. So we're going to go to our Desmos calculator, clear out what we don't need. Oops, I could have kept that, I guess. Here, let me get a new table. Careful as you enter. 24.9. And I truly hope that you guys are trying this on your own and not just continuing to watch me to do it, because you need to start to feel what it feels like, right? Do it yourself and press play if you get lost or need help. And let's do the regression. So y1, remember this is quadratic, so we need to put in a quadratic equation. But don't forget your sub 1, because remember that little sub 1 matches our data up here, our data table. Squared. I just did caret and 2 plus bx sub 1 plus c. There it is. Let me get, here we go. And I'm just going to snip this and bring it back to our presentation for us. There is our quadratic regression line. So again, it kind of sounds a little bit scary, maybe, but it's hopefully not too bad. And as you guys practice it, you're going to remember, oops, the y hat equation. Why is it doing this to me? Do you guys see what it's doing? There, okay. Remember, quadratic is ax squared plus bx plus c. So here is our prediction line. And it doesn't say what to round here, so that's interesting. We'll just do the thousands place again. So 886 minus 6.364 plus 24.736. There we go. All right, you guys. I hope that you have a wonderful spring break, and don't forget about your benchmarks next week, and just reach out if you guys need anything. Bye, everybody.